Assalamualaikum viewers, please like, share and subscribe this channel. Links of PDF files used in this video are given in description. So today's lecture is about structure of metal carbonyls, and in this lecture we will mainly focus on mononuclear molecules such as Chromium Hexa Carbonyl, Iron-Penta Carbonyl and Nickel Tetra Carbonyl. So this is the overall hexacarbonyl chromium complex. As there is no species outside of the complex, it means the charge is neutral. The carbonyls are neutrals, that is why chromium is also neutral. So this is the atomic number of chromium and this is the valence shell configuration of chromium. Although the configuration is 4s2 3d4, but in order to gain stability we have a stable configuration which is 4s1 3d5. Now this configuration, valence shell electronic configuration, has been written in this form according to valence band hybridization theory. So the 3d orbital has been written first, then 4s and 4p. So 4s1 3d5 is the electronic configuration. Now what is happening here, that as according to crystal field theory, this carbonyl is a strong field ligand. So what we will do, we will pair up these electrons in the inner orbitals to get more stable rearrangement. So the rearrangement has been shown by drawing a star on the chromium. So we are seeing all the electrons has come in the lower orbital and they have now become in paired form. As a result of this pairing and rearrangement, now we are seeing that further the orbitals have been become empty. Now as we have to attach 6 carbonyls with the chromium, so 6 empty orbitals which are 2 d orbitals, 1 s and 3 p orbitals, they will combine together and undergo hybridization to generate 6 d2 sp3 empty hybrid orbitals. So 6 carbonyls will be attached by donating their lone pair towards these empty d2 sp3 hybrid orbitals to form 6 coordinate covalent bonds. And we all know very well that the geometry of d2 sp3 hybridization is octahedral as shown in this diagram. But the basic purpose of this lecture is not to understood the concept of hybridization, but the concept to develop here is the bonding situation and then the concept of back bonding. So we have completed that. Okay, this is having a octahedral geometry. Now we will again start from here and we will see how the bonding situation actually lies. So if we ignore the concept of hybridization and we see here that there are 6 carbonyls that have been attached to the chromium. Now the green electrons with cross, these are purely of carbonyl that have been donated, and we all know very well from the previous lecture that this lone pair which has been donated by carbonyl is present in the sp orbital of carbon. Now we are seeing here that 6 sigma bonds have been formed. Now as in the previous lectures we have seen that there is concept of back bonding, and if there is no back bonding then we know structure A will be the predominant form, whereas if there is back bonding as shown here then structure B will be predominant. So in order to represent this, now how we can show this back bonding in valence bond theory diagram. So as there are total number of 6 carbonyls attached, so when there is even number, so what we will do, that we will do 3 such carbonyls which undergo back bonding, or 3 carbonyls will be in B form, whereas 3 carbonyls or half of the carbonyls will be in A form. So in A form, as there is donation towards the chromium, so there is no back bonding, whereas in these 3 remaining carbonyls there is back bonding, and the chromium back donate its electrons to the carbon of carbonyl through a pi coordinate covalent bond. So in this way, now we have represented that in three carbonyls there is the case where there is no back bonding, whereas three carbonyls they show back bonding. So in diagram which is here represented, that is the diagram of chromium hexa carbonyl with octahedral geometry, we can represent that these carbonyls, at least three of them are attached with metal through pi bond 2, whereas three are only attached with sigma coordinate covalent bond. Now why we are not showing that pi bond in this geometry is the reason that pi bond is not explained in hybridization theory. Hybridization theory is saying that pi bond is not involved in hybridization. That is why, as we have drawn this diagram from this hybridization theory, so we will not include or draw pi bonds in these geometries. But in bonding situation, we know that three carbonyls are such like that there is no back bonding, and three carbonyls are such that there is back bonding. So we can say three carbonyls are attached with chromium with B form and three are attached with A form. Now what is the evidence behind this? The evidence comes from the stretching frequencies in IR spectrum, and which have been we have been studied that IR structures in detail in the previous lecture. Now let's see quickly how the nickel tetra carbonyl bonding situation can be explained. So again, there is no species outside of the coordination complex. Charge is 0, carbonyl is 0, so it means nickel is 0. This is the atomic number of nickel, and this is the valence shell electronic configuration of nickel. Now in terms of VBT, we can write this configuration like this. This is 3D, 8, 4s2 and 4p0 electronic configuration. Now again, we are seeing here that there is carbonyl and it is a strong field ligand, so we will pair up the electrons back in the 3D orbital, and now we have this rearranged form as shown by this steric, and now the configuration is that 3D has been completely filled, whereas 4 has become empty. Now as there are 4 carbonyls attached, so we need 4 empty orbitals, 1s and 3p orbitals, so they join together, undergo hybridization to form 4 empty sp3 hybrid orbitals, and 4 carbonyls are attached through sigma coordinate covalent bond, and the lone pair is donated by the carbonyl through its sp hybrid orbital. Now in terms of back bonding, we can explain this structure as, again there are 4 or even number of carbonyls attached. So again, by relying on a general rule that if there are even number of carbonyls, then we will do half carbonyls with no back bonding and half carbonyls will be attached with back bonding. So here 4 sigma bonds have been formed, but in these 2 are with A form with no back bonding, and 2 carbonyls are in B form with back bonding, and in back bonding the pi electrons are donated towards the carbonyl through pi coordinate covalent bond. So the geometry of this complex is tetrahedral geometry. A little detail or addition is that this orbital also contains 2 electrons donated from the carbonyl. Next, let's see the geometry of Iron-Penta Carbonyl. Again, there is no species outside of the coordination complex, so this complex is neutral. Carbonyl is neutral, then iron is neutral. So this is the atomic number of iron, which is 26, and this is the valence shell electronic configuration, which is 4s2 3d6. Now this configuration has been written like in the form of valence bond theory. So 3d, 4s and 4p. 3d contains 6 electrons, whereas 4s contain 2 electrons. Again, carbonyl is a strong field ligand, so all electrons will be paired up, and this is the rearranged form shown by a steric. Now the 3d contains 8 electrons. So in this way, 2 new orbitals have become available for hybridization. So as there are 5 carbonyls that has to be attached, so 5 orbitals including 1d, 1s and 3p orbitals, they join together and undergo hybridization to form 5 empty dsp3 hybrid orbitals as shown here. So 5 carbonyls, by giving their lone pair which is present in sp orbital, they form 5 coordinated covalent bonds. Now the geometry of this hybridization is trigonal bipyramidal. Like these three coordinate covalent bonds, they are planar, and these two are axial. So in this way a trigonal bipyramidal geometry is formed. Now let's see the bonding situation here. Now this is the first case in which there are odd number of carbonyls attached. In the previous lectures we have seen even number, and what we have followed a rule that if there are even number of carbonyls, then in half we will do back bonding and in half there will be no back bonding. But if the number of carbonyls attached in this example, like if they are odd, then in two carbonyls we will not do any back bonding, whereas in remaining orbitals we will do back bonding. So if there is number of carbonyls attached are 5, then in 2 we will do no back bonding and they will be in A form as shown here, whereas in 3 we will do back bonding. So overall we are seeing that 5 carbonyls are attached and donate its lone pairs to form 5 sigma bonds, but 2 are in A form with no back bonding, and 3 there is a pi bond formed by the overlap of the filled orbital of metal with empty pi star orbital of carbonyl, and the charge density is back donated towards these carbonyl through pi coordinate covalent bond. So this is the bonding situation of trigonal bipyramidal geometry Iron-Penta Carbonyl. All these examples were those cases in which the coordination complexes were mononuclear, like the metals were only one atom of metal that was surrounded by a number of carbonyls. In the next lecture, we will see some bonding situations in multinuclear metal carbonyls where there are more than one number of central metal atom or ion. So this was all about today's lecture. I hope you have well understood this lecture, but if you have confusion or have some question or query in your mind, please write in the comment section and I will respond to that query as soon as possible. Okay, thank you. Allah Hafiz.